Yeah, so we are starting now. Respected senior EC members of INS, friends and participants who have joined online today for this webinar. I welcome you all to this webinar. As you know, this is the 13th webinar in the series. We invite eminent speakers to give talk on subjects of relevance in science and engineering. And today we have fortunate to have Professor J.Srinivasan, Emeritus Professor and founder of Divecha Center for Climate Change, which is operating in the ISC campus. He's going to talk to us on science of climate change. And on behalf of INS, I welcome you, sir, for this webinar. So we are delighted to hear you. And I'm sure that we will be greatly benefited to learn from you about the science of climate change, which is very important, relevant today as we stand to acknowledge that the climate change and its effect on the future life of this planet. The whole world is engaged with the topic and the seriousness of this topic, which could be one of the biggest crises of mankind that is facing. So climate must have been perpetually changing over the centuries. I'm sure about this. But the question is how mankind is influencing the climate change. What is the past, present, and the future of climate change? So Professor Srinivasan is going to talk to us on this and challenges to arrest the change for the good of the mankind. I once again welcome Professor Srinivasan to this webinar. And I now invite our President S.K. Mehta to give his opening remark. Mehta, sir.
Thank you. Thanks a lot. Professor Srinivasan, great welcome to you to this INS webinar, The Science of Climate Change. In fact, the climate change is changing faster than the science, the knowledge that we are trying to gather about. And I think we are very happy to have you and to learn about these climate changes that come there. I'm glad that you are from the Indian Institute of Science, where I had my first training in the nuclear engineering in 1957. So I will be happy to hear you and share your views on the various aspects of science and technology. Thank you very much. Welcome again.
Thank you, sir. Ramanamurthy, can you introduce the speaker, please?
Yeah, thank you, Mr. Ramarao. It's now my pleasant duty to just read out a brief profile of Professor Srinivasan. Professor Srinivasan established the Divecha Center for Climate Change at Indian Institute of Science, Bangalore in 2009. He has obtained BTech from IIT Madras, MS from State University of New York, and PhD from Stanford University. He was the chairman of the Center for Atmospheric and Oceanic Sciences from 1997 to 2005, and chairman Mechanical Sciences Division from 2005 to 2009 at Indian Institute of Science. He was Senior Resident Research Associate at NASA Langley from 1993 to 1995. He was a lead author of the second and fourth IPCC reports on climate change and the review editor of third IPCC report on climate change. He was the principal investigator of the Indo-French satellite mission Make Tropics, which was launched in October 2011. He has published more than 140 research papers in climate and thermal sciences. He is the fellow of the Indian Academy of Sciences, Indian National Science Academy, Indian National Academy of Engineering, and the World Academy of Art and Science. He was a J.C. Bose National Research Fellow during 2007 to 2012. He received the Lifetime Achievement Award of the Ministry of Earth Sciences in 2019. His major scientific contributions are in the area of monsoon models, impacts of aerosols on climate, and impacts of clouds on Earth's radiation budget. So with this introduction, now it's my pleasure to welcome Mr. Srinivasan to commence his presentation. He's going to tell us how on earth we are going to save this earth. Over to you, Mr. Srinivasan.
Thank you, Dr. Ramarao, Dr. Mehta, and Dr. Ramanamurthy for inviting me to give a talk. Now, let me switch off my video so that more bandwidth. I've been giving talks on climate change for the last 35 years. And very often I find a lot of intelligent and highly educated people are climate skeptics. That is, they don't think climate change is a serious issue. Let me give one example. The best example is, all of you have heard of David Attenborough, one of the most famous naturalists, who has made many good videos on the natural world. He said, I was skeptical about climate change about 10 years ago. And he said, I was cautious about trying both, but I'm no longer skeptical. So this is very interesting that a lot of people, I can name a few people in India, even Professor Siana Rao was a skeptic. And many more I can name, chemists, physicists, even engineers. And that is partly because if you look at the Earth system, its climate is controlled by many things, not just what we do. Okay. So naturally, the question is, when sun's output controls climate, when the sun has geometry, and some people believe even stellar deaths, I don't believe it, but there are people who believe that also affects us. And all the internal factors inside, that is volcanoes, mountain building, drift of continents, heat transfer with ocean, reflectivity of the surface, reflective atmosphere, and chemistry, all these influence. So naturally, the question is, how can we model such a complex system and be confident that the Earth's climate is changing on account of human beings? So I can tell you that 35 years back, our knowledge was not that good. When I gave talks, people asked tough questions, and I did not have answers at that time. But now, in the last 35 years, the amount of research that has been done, especially about the past climate, which has helped us understand the complex Earth system and able to model it. So that's why now our confidence in our ability to predict the future is better than what it was 35 years ago. But of course, still there are a lot of people whom I call climate change deniers. That is, who believe there's no global warming, humans are not responsible, but that even is occurring, its impact is not important. And sometimes they say even the impact is large, it will cost too much to mitigate. All these are wrong, of course. So my job is to first tell you how much of the Earth's climate we understand, its natural factors is control it, and how human beings influence it. And finally, how we can mitigate climate change without paying a very high cost for it. Now, this year, climate science got a big boost because of the Nobel Prize in Physics given to two other people, Klaus Hasselmann and Professor Manabe from Princeton. So both these people got the prize because they were involved in modeling the Earth's climate and able to do a fairly good job that today the IPCC is able to predict with some confidence how much the Earth will warm in the next 70 years or 80 years. Now, one must remember that Earth's climate change issue is what sociologists call a wicked problem. A wicked problem is one in which the society response is one of avoidance and denial, because the way you want to control the emissions of human beings involves major sacrifices, major changes. So one tries to avoid when you have to deal with difficult changes. So there's no change in the behavior response until there's a crisis. Okay, and of course there's an ethical issue. All the things we have done in the last 100 years for rapid economic development is going to affect the future generations. And so we need to now take that into account, not just be fair to people living on Earth today, but be fair to people who are going to be on Earth 50, 100 years from now. That's a tough thing to convince people that you have to do something now. The benefit will come to somebody else 50 years from now. So I'm going to talk about how climate change in the past, how human beings influence our present climate, and how it will change in the future. Now, the reason why there is a lot of doubts about climate issues is because among many people, there's a confusion between weather natural climate variation and human-induced climate change. So if you confuse between them, of course, then you cannot understand which is important, which is not important. Now, the first thing to remember is that weather is a very short-term phenomena. We're talking about days to weeks. Climate variability is the change in climate from year to year due to natural causes. And that we have to accept it and we have to live within that variation. And climate change can occur, of course, due to natural causes. But right now, when we say climate change, we mean human-induced climate change, which is occurring over a longer period of the order of 50 to 100 years. Okay. So, but there is interaction between them. They're not, although they are defined in different time scales here, each one of them does influence the other. And so that we have to understand. Now, weather is something all of us understand because every day when we go out of our house, we have to decide what dress to wear. So we do worry about what is the present weather. But climate is the statistics of the weather. So it is influenced not by the just atmosphere, which is enough if you want to predict weather, but we want to know also about what's happening in the ocean, land, and what human beings are also doing. So climate is more complex than weather because it is the statistics of the weather we are talking about. To make that point clear, I want to take an example of two cities I've lived in, Chennai and Bangalore. You see here the maximum temperature in Bengaluru in blue and in Chennai in brown here, distribution over about 45 years of daily data. Now you see that the climate of Bangalore and Chennai is very different. Bangalore is about 6 degrees cooler than Chennai on an average. But on any given day, the weather of Chennai and Bangalore may be similar. Right, you can see where the pointer is shown. There are some days, especially in March, where Bangalore is as hot as Chennai. So that is daily weather. Sometimes they can be similar, but the climate is very different. Now, climate changes due to natural causes, but now we are changing climate due to our actions. So that distinction one has to make. Secondly, the confusion that occurs a lot is between local and global. The focus of I talk will be on global climate change because the agreement in Paris and the subsequent negotiation in Glasgow are connected to global climate change. But all of us don't live in the globe, we live locally. So all of us are concerned about what happened to climate in Mumbai or in Bengaluru. But you must remember that local climate is not only influenced by global climate, it's also influenced by what happens to that place. For example, Bangalore has become much hotter than the surrounding rural areas because of urban heat island effect. So when you talk about local climate change, you have to worry about factors other than greenhouse gases. Okay. Now to illustrate that, I'll give an example of only one station in the world where you have data for around 250 years or 228 years to be, 248 years. That is in central England, they have measured temperatures for a long time. That is the black line, okay? And it has been slightly smoothened so that it doesn't look too noisy. And the red line is the global mean temperature, which we can calculate from 1850 with some, of course, confidence. Not always very accurate earlier, but now it's very confident. You see that the local climate change in central England is varying much more than the global climate, because local climate is influenced by local factors also. So, but the focus I will be making only on global climate because that is easier to explain, and that's what we are trying to control in this global negotiation. Okay. Now, let me first show you why we are concerned. So look at the global mean temperature of the last 100 years, that's a black line here. That is going up at the rate of more than 1 degree per 100 years. The previous 1,800 years, the temperature was gradually declining, very, very slowly, okay? Now, you might ask, who measured this temperature? Because thermometer was invented only in 18th century. So this is called reconstructed temperature. This is based mostly on tree rings. You look at tree ring data and infer the temperature. It is not a perfect thermometer, but it's quite good. There's an error bar you can see here. It is not perfect, but it clearly shows that the temperatures were slowly declining before human intervention changed the direction. I want you to see the slope difference. The natural climate variation is very, very slow, while the human-induced climate change is very rapid. So that's a point you have to remember, because a lot of people ask me, why are you so worried about 1 degree? 1 degree is nothing. 1 degree compared to the difference between minimum maximum temperature in Bangalore or difference between winter and summer is very small. But the key issue here is not the amount of temperature change, but the rate of change. Okay. Now, just to give you this one, all the past climate I'm going to talk about in the next 10 minutes is related to use of tree rings or ice cores or lake sediments or coral reefs or ocean sediments and coastal sediments. Now, this is a very specialized area. I'm not an expert in it. This is called Proxy Evidence. A lot of people all over the world, including in India, have worked on it. And initially, I was very skeptical, because when you try to infer the temperature from tree rings, you are assuming that temperature is the only parameter controlling the ring width, which is not true. There are other factors. Rainfall plays a role and other things play a role. So I was always skeptical when people showed me data from proxy. But today, the advantage is that the subject has developed rapidly, and we have multi-proxies. That is, temperatures inferred from many data, not just tree rings, also ice core, also lake sediment. Each of them is a different method. So if all of them agree that temperature was warmer at some time, then we can be confident, because they are completely independent ways of inferring past climate. Now, based on that, we can mention what is the temperature was during the last 22,000 years. Okay. And this is truly remarkable. I'm always impressed by what these paleoclimatologists can do. So they tell us that temperature during the last ice age was 7 degrees lower than today, global mean. And then it rapidly increased, natural cause, rapidly increased over about 8,000 years to almost close to the present temperature in the 19th century. And so this change was 1 degree in 1,000 years. So note that natural climate change is very large, can be 8 degrees, but it, at the rate of 1 degree per 1,000 years. Okay. So the key point is that natural climate change is slow, and the human-induced climate change is 10 times faster, and many biological beings and mammals and insects and others will have difficulty to adjust to a rapid climate change. That's one of the biggest concerns all of us have. Now, just to show you what these people can infer from the long time, past 60 million years, okay, based on oxygen isotope data, they indicate that the deep ocean temperature was about 12 degrees warmer than the present. And then it started cooling due to various causes, including the rise of the Himalayas. And then the Antarctic ice sheet formed about 40 million years ago. And the temperature kept declining. So Earth was quite warm most of the time. As a matter of fact, all the oil, gas, and coal you're using today was produced at this time, this warm period. Okay, and so we have benefited from that warm period, but now we are overdoing that exploitation of that resource. Now, briefly to explain the factors that control global temperature, there are only two. One is the amount of solar radiation absorbed by the Earth is controlled only by the snow and ice cover on Earth. If the snow and ice cover is large, as it was during the ice age, the Earth absorbs less, temperature goes down. Okay, and the key point about Earth is water appears in three forms: vapor, liquid, and solid, and the properties are very different. Vapor hardly scatters any visible light, while ice is very good, 90%, and water is almost a perfect absorber. So this large difference in reflectivity between ice and water is what controls Earth's temperature, because huge difference. Typically, when 1 square kilometer of ice melts, the amount of radiation absorbed goes up 9 times. So that's the dramatic change we have seen in this century. Now, the other part about Earth is very unique. 99.9% of the gases on Earth do not absorb either solar radiation or the Earth's radiation. Okay, so are completely transparent to both, and that's why Earth's climate is controlled by minor gases. This many people do not, especially those who are not scientists, do not understand. How can a gas with whose amount is 0.04% can control Earth's climate? It is doing that because the major gases are doing nothing. So these four minor gases, carbon dioxide, water vapor, methane, and ozone, absorb the radiation emitted by the Earth and control the Earth's temperature. Okay, so this I'm sure all the people in this audience know well. Now, so the Earth's temperature is obtained by a balance between amount absorbed and amount emitted. Both are functions of temperature, and so we look at this balance graphically. So graphically, I've shown you this balance as a function of the Earth's temperature. The dotted line is the emitted radiation, which slowly increases with temperature. And the absorbed radiation, which is a function of the amount of ice, that varies in a very unusual way. When the ice cover is large at low temperature of the Earth, when the Earth is almost completely ice covered, absorption is only 100 watts per meter squared. But today, when the ice cover is very small, absorption is 240 watts per meter squared. So a difference of 2.4. And in the last ice age, it was about 180 watts per meter squared. So the key point about this result, which is graphical, shows you three solutions for the present incoming radiation from the sun, which we have measured accurately from satellites. Now, what this equation says that for the present input radiation, there are three possible states, out of which this is very unstable. One can show very easily by stability analysis unstable state. So it remains here for a short time and then either moves to this state or to the completely ice-covered state. The question is, why are we here and not here or there? Of course, we were in this ice age about 20,000 years ago, and we have moved to this state. Now that we understand that the Earth's climate is not stable, we need to be careful. Because what will happen if you push the Earth by increasing carbon dioxide monotonic it for the last 100 years and we continue on, it may go to another state as the ice melts more and more. That is a cause for concern. And the Earth is sufficiently complex that we cannot say with great confidence what perturbation the Earth can withstand. There are still debates among the climate community whether it is 2 degrees or 1.5. So in Paris, the agreement was we try to keep it below 2, but preferably below 1.5. But that is not a what do you call perfect number. We don't know the number. We know that the Earth's climate is very stable during the last 10,000 years, and it didn't vary more than half a degree centigrade year to year. So if you go beyond 1 degree, one cannot be sure where the Earth will reach. Now, we also have evidence from geology that the Earth was completely ice-covered once. Now, this is remarkable. If you're interested in this, you should invite somebody to talk to you about this. It's called the Snowball Earth. It was only discovered 15 years ago based on geological evidence in Africa that up to the equator, the ice had reached. That is 1 billion years ago. And of course, there was a period when Earth was completely ice-free. That also happened. So what it says is that the Earth climate can oscillate between ice-free to ice-covered to partly ice-covered. And it happens quite suddenly. It remains in one state for a long time and then shifts to another state. So this is best explained by mechanical analogy because I'm a mechanical engineer. The analogy is we are in the present interglacial. We are in a fairly stable climate, but we perturb the Earth's temperature too much due to our actions. We can shift it not to glacial because all the ice melting, to another state on the right, which is the much warmer state where Earth will be completely ice-free. Okay, I'll mention that again at the end. Now, let me tell you what we have learned about the Earth's climate during the last almost million years through ice cores in Antarctica. Now, engineers, scientists went in the 60s to Arctic and Antarctic and found ice layers almost 4 kilometers thick. and they drilled all the way through. It's amazing. And they had to take out this ice core, and this is an example of that ice core. And in the ice core, they saw air bubbles. So these air bubbles are the bubbles which are trapped after the snow is compressed and made into ice. And this air tells you what was the composition of the atmosphere thousands of years ago. This is an amazing achievement. Remember, you take this ice core to the laboratory, use a hypodermic needle and carefully take out a sample of air without contaminating it with the surrounding air. It is truly remarkable engineering feat. And through that, we have found out, so these are the snow particles which get compressed, and then it is sealed, the air is sealed here for thousands of years, okay, in the lower reaches. Based on that, more than 40 years ago, people published papers showing that in the last 400,000 years, Earth went through 4 major ice ages, where the temperature was 10 degrees below present. Okay, the last ice age ended about 20,000 years ago. Here, right here. Okay, so there were a few warm periods, very short ones. Warm period was not stable. Remember that. So it tended to go back to the ice age. And of course, there are theories why that happened. I will only mention it briefly. Now, what this says is that Earth climate is not stable. It oscillates, and it oscillates a lot, and sometimes it jumps into a new state, which is warm for a short time and comes out. Now, the reason why this is important for us human beings is we mammals prefer to live in a warm climate, especially after we discovered agriculture 10,000 years ago. We need a warm climate, otherwise agriculture cannot survive. Okay, so remember that during the period 20,000 years ago, when there was no agriculture, the only people who survived are cave dwellers, and very small amount in people in thousands or 100,000 people, that's all. So only after we came out of the last ice age and had a long warm period of 10,000 years, that human population grew rapidly. Now here is the data for 800,000 years, showing more number of ice ages. But the key thing here is comparing the carbon dioxide content in the air bubble with the temperature in that ice obtained from deuterium isotopes, and they go together. That is a beautiful result, that the temperature of the ice and the amount of CO2 in the ice are coupled very closely. They are not independent. Okay, so that shows clearly that either CO2 controls the temperature or temperature controls CO2. We cannot differentiate very easily, because when you take a sample of 800,000 years, your error in measurement of time, which is measured by radioactive decay and so on, is of the order of 1,000 years. So you cannot be very sure about which is the cause, which is the effect. What you are seeing is only association. So I put the two figures together, and it is remarkable that the amount of CO2 and the temperature vary so closely. Okay, first thing. Second thing, notice that the last portion is the last 100 years. That is a nonlinear scale here. In the previous 400,000 years, notice that the amount of carbon dioxide in the atmosphere, when human beings were not around, was controlled to be between 280 and 200 by natural processes. What this shows is that Earth's natural climate is delicately balanced by various factors, so that the amount of CO2 does not go below 200 or above 280. But now we human beings have perturbed this Earth climate so that we are well above what was there in the last 400,000 years. Now we know for the past 4 million years. Recently, somebody found that 4 million years ago, carbon dioxide may have been above 400 ppm. Okay. Now, most recently, there was a very nice paper published by Shakun et al. In Nature, where they were able to get more accurate data for the last 20,000 years, and they showed that first, the temperature in Antarctica started increasing. That is a red line. Okay. And when the temperature in Antarctica increased, due to solar radiation impinging more on Antarctica, the carbon dioxide went up in Antarctica. And finally, the change in Antarctica triggered global changes, and about few thousand years later, the temperature of the Earth increased. So now we have a clear evidence to show that in the past, CO2 increased first and the temperature increased later. So this, to me, is a very neat proof that CO2 is the controller of Earth's climate. And it is what the ecologists call keystone species. In every ecosystem, there's one particular animal which controls the ecosystem. So in the Earth's atmosphere, Earth's climate, CO2 is the keystone gas. That is, its composition controls the climate. So Earth's climate is controlled by not only CO2, also by methane and ozone, and also water vapor, because water vapor is a very strong greenhouse gas. But water vapor is something which we cannot independently control, because all of you know it depends on temperature. So Clashes-Clapeyron equation dictates that water vapor in the atmosphere is controlled by temperature. So today the water vapor on Earth is about 7% more than in 1850 because of temperature rise. So we cannot have a global negotiation to control water vapor, because that's not in our control. We can control CO2 because it doesn't condense. So of the four gases I mentioned here, carbon dioxide, methane, and ozone don't condense. Water vapor condenses. So its concentration depends on temperature, while others, they don't. So just to summarize what happened in the past, due to changes in Earth's geometry, solar radiation, the polar region changed, and that caused, for example, in the recent past, more melting. And when the temperature went up, carbon dioxide came out of ocean, water vapor came out of ocean land, methane came out of soil, and all caused more greenhouse effect, and which further increased temperature. At the same time, ice started melting in the polar region, and water absorbed more solar region. So two positive feedbacks led to a rapid change in temperature. So we can now explain very clearly how the temperature of the Earth increased by around 8 degrees during the last 20,000 years. And people have done climate models which reproduce the proxy data quite well. So we know that we understand quite well how Earth's climate changed in the last 20,000 years. Even though human beings are not there, changes occurred, but they occurred slowly, okay, due to these two chain reactions. So what we have learned from that is that Earth system is capable of abruptly jumping from one climate state to another, okay? So we cannot be very casual. But what happened really was, about 50 years ago, people had looked at only last 10,000 years. Last 10,000 years, Earth's temperature was very stable. This is the blue line, okay? So they thought Earth's temperature is stable, nothing can change it. Today we know that's not true. Today we have good data going back to the last ice age and beyond. We know that Earth's system is not stable, so we need to be careful not to put up the climate beyond a certain point, okay? Now, one example during this period, 20,000 years, there are rapid fluctuation occurring in the northern hemisphere called the Boiling-Ellerod and Younger Dryas. This was a sudden warm event, and then it suddenly cooled. These are events which changed the temperature locally in a matter of 10 years, okay? For example, carbon dioxide increased in this region by 20 ppm in 200 years, okay? That's quite fast. But of course, we are now increasing it by 20 ppm in 10 years. Again, we are doing it faster by a factor of easily 10 or 100, okay? So, but abrupt climate change has occurred in the past, in the recent past, I'm talking about 15,000 years ago, and it can again happen in the future. Now, to bring that point clearly, I've shown the carbon dioxide concentration from 1,000 years ago to 1800, almost stable at 280. Now, once the extraction of coal and oil starts, you can see there's a rapid increase, okay? And in the last 100 years, we have much more accurate data, and it is increasing even more rapidly. So this is the cause of concern, the very rapid exponential increase in carbon dioxide, methane, and ozone in the atmosphere. Now let's look at last 100 years. Now this graph shows the rapid change since 1980. can see it's very rapid because this is a temperature anomaly, that is, we subtracted the mean in this period, which is the normal period chosen for 1951 to 80 period we choose for a mean value, which is around 15 degrees centigrade. You subtract that. So you can see that Earth was about 0.5 degree colder than this time, and now it's about 1 degree warmer. So total 1.4 degree increase since pre-industrial. Okay, that is what has already happened, and that is primarily on account of human activity. Now the problem is the land is warming faster than the ocean because land has very low heat capacity. So land has already gone up by 1.6, 1.7 degrees centigrade. The ocean is absorbing all the heat, but it is rising more slowly, but it will continue to rise because it has the heat capacity in it. Now, many people say 1 degree warming is not to worry about, it's not much. But you must notice that the Arctic region has already warmed by 4 degrees. And many parts of the Arctic are more than 4 degrees warmer today, and this is leading to dramatic changes in the Arctic region, which I'll talk about very soon. Okay. So reminding again that global temperature is increasing 10 times faster than it has in the past 20,000 years. Okay, let's look at the impact. Now, to study the impact of this on climate change, we need models because there are various things going on Earth. We are not sure if these are caused by human actions or natural causes. So we need a model. And in the last 50 years, because of the advent of the computer and development of the numerical models for the atmosphere and ocean, we are able to run complex climate models for the entire Earth, both for the land and the ocean, as well as vegetation and ice and so on. So this is the development which has been remarkable. And almost all the countries in the world run these models routinely, both for weather forecasting and climate change. Same model is used, no different model. So one must remember that since the Earth system is complex, in every climate model, there are some approximations, and this can cause serious errors in certain situations. So people, when we talk about negative impact, they say, how do we know your model is not perfect? That's true. We cannot deny that. But one must remember that these climate models are quite accurate at a global mean scale, on a larger scale. It may not be accurate for Mumbai or Bengaluru. It will be quite accurate at all India scale, on a hemispherical scale as well as global scale. Here's an example. There are about 30 models here, 36 models. All have been run for the last 100 years. And the CO2 was allowed to increase in the model as per observation. And each model output is shown in thin lines here, various colors. The red line is the mean of all the models. There are 114 simulations. You average over all of them to remove the noise. And the black is the observation tabulated by the UK Met Office. Okay. And you can see that the red and black lines move in a similar way. They're not perfect. You can see that year-to-year variation, the climate models don't capture too well. Okay. That's not surprising, but year-to-year variation to capture, you must exactly capture the heat exchange with the ocean and atmosphere, which still is not very accurate. But if you average over 5 years, then these two are almost perfectly matching. It is showing that temperatures are approximately constant up to 1960, and then it started rising. And some of the cooling that you see here are due to volcanic eruption. There was one major one in the 60s, Agum, and there was another one in 91 in Pinatubo. So two of these cause cooling of the order of 0.5 degrees, and the model is able to capture that. So we know that model, in spite of its approximation, is good at getting global mean temperature. Now in this model, if I don't allow CO2 to increase, then I get these orange simulations of many models. Okay. So what this model shows clearly, beyond reasonable doubt, that this warming after 1960 is only on account of CO2 increase, because the red line is the simulation average over all the models with CO2 increase, and the orange lines are modeled with no CO2 increase, CO2 kept at 280 parts per million. So this shows beyond reasonable doubt that human beings have caused the change over the last 60 years at least. Now, but still, when you look at the models for the future, there are problems. Now, here I've compared 12 different models from many countries in which CO2 was doubled, and then they looked at the temperature change globally. One model is saying 2 degrees, one model is saying 5 degrees. Now, that's a cause for concern, and we know why. The last 20, 30 years, all of us have worked on these models, and we know that the biggest mistake in the model is about clouds. Now, these models, which are run for hundreds of years, the model resolution is only about 50 kilometers, X and Y, that is latitude, longitude. You cannot go to high resolution because of it requires more computer time. So what happens in this model is a typical cloud in the Earth's atmosphere has a scale of about a kilometer or a few kilometers. So we cannot simulate that from first principles. So all these models put into cloud empirically. That is, the models say that if the 100 by 100 kilometer average humidity and temperature are above a certain value, it will rain. That is completely empirical. It is not based on first principles. Now, each model uses a different empirical technique depending on which part of the world it is developed. Because these models are developed for weather forecasting, and they tune the model to agree with the local forecast. Okay, so there's a range of variation of the order of 3 degrees, which is unavoidable. Okay, so what I would say is when we predict future climate to warm by 2 to 3 degrees, there is an error of about plus or minus 1 degree, which is to be accepted. But what you must remember is, if you ask what will be the Earth's climate by the year 2100, the major uncertainty is not in the model. It is in what we will do in the next 80 years. The emission scenario, whether we will allow CO2 to increase or CO2 to decrease. So this is the point. The point is, remember that future the Earth's climate is under our control. Okay, in spite of model uncertainties, which is about 20%, we can predict the future, provided we know what kind of emission scenario we follow. That's why the debate in all these meetings which are held every year, the committee of parties, is to decide how to control the emissions. Because if we control the emissions, we can bring it down to a very low value, the uncertainty. Okay. So let me summarize what's happening in the last 100 years. Last 100 years, the main increase in temperature on account of human being increasing CO2, that increased the temperature, water vapor came out of the ocean and land, and so the greenhouse effect of water vapor added to CO2, greenhouse effect, and of course ice melted. So the key thing now is the feedback from water vapor and ice melting. Now I must tell you that Professor Manabe, who got the Nobel Prize this year, he discovered this particular route. He showed with a model that if you keep water vapor constant, then the temperature rise is much less. This was done more than 50 years ago. And at that time, people were really surprised at the role of water vapor. Okay. Now let's look at what kind of impact is there. Again, people say 1 degree warming is not much. Yes, 1 degree is a shift in the distribution. Dotted line is the temperature which existed, let's say, 50 years ago, and solid line temperature distribution today. You can see that just a 1 degree shift gives you a lot of days with extremely hot climate, which was not there before. So these are all new temperatures, records which are being established all over the world because your distribution has shifted ever so slightly. Okay. So Klaus Hasselmann pointed out more than 50 years ago that we should worry more about extreme events than the mean, because that will have the strongest impacts on our living. And he's absolutely right. Today, what we have to worry about in India is how the number of hot days in summer is going to increase in the next 50 years. Okay? We live already in a hot climate, and if the temperature goes up another 3-4 degrees, many parts of India will be unlivable, especially for people who work in factories and in agriculture. They cannot work if the temperature goes about 37, 38 and humidity goes up. They cannot survive. Okay, so that is a point we have to worry about. Okay. Now, data shows that extremely high temperatures were gone up 50 times area-wise in the last 50 years. The area covered by globe where temperature high has gone up 50 times, and it will continue to increase more and more because of this warming. And the second part which comes in automatically is because of the higher temperature, evaporation is higher, so the water stress goes up. So the country most affected by global warming will be India. China is somewhat colder, so they will not be affected that much. India will be the most affected country in terms of water stress because evaporation will occur more, so we'll pump more water from groundwater, and we're already facing stress. The stress will increase further. And remember that when heat and humidity are combined, there are limits for human beings. Our core body temperature cannot exceed 37. If the ambient temperature goes above 37, we can sweat. But if the ambient humidity becomes 100% and the specific humidity of the air outside is higher than the specific humidity of my skin, air and next skin, I cannot give out the heat. And this is called heat death. And it will happen. And people have shown that even young people, when they work hard under hot, humid conditions, they die due to heat death. Now, just last year, we had a record in British Columbia. I'm sure most of you know British Columbia is in mid-latitude region, but temperature never goes to 49.6. This kind of temperature you only remember in Saudi Arabia or Dubai. But that happened in Lytton for a few days, and that is one extreme event. Okay, temperature was rising naturally due to the seasonal cycle, but due to a weather phenomena called the heat dome, temperature went up by 10 degrees above normal. Okay, so this is going to happen more and more often, this kind of extreme events. And so how do you know that? Now today, because we have climate models, we can run the model twice. One, run the model with CO2 increase, and one without CO2 increase. And people ran it and showed that this 49.6 occurrence is 150 times more likely because of CO2 increase. It can also occur without CO2 increase, but chances are very low. So what's happening is extreme events which can occur naturally are occurring more often now by a factor of 100. So this is the major threat to human beings. So this can now be quantified. Now there are papers published every day. You know, they run a model 2 times, one with CO2, one with increase, and they look at each extreme event and attribute. It's called attribution. They attribute how much is due to increase in CO2. For example, heat. When there is a heat wave in the last 15 years here, every heat wave was looked at, and they showed that out of the 60 heat waves, 52, 53 were higher because of CO2 increase. Droughts, about half of them were due to CO2 increase. Heavy rainfall, about half. And ocean heat waves, about 90%. So we can clearly attribute what increase is due to CO2 increase. Now let me tell you a little story which is worth remembering. About 12 years ago, we had an Indo-Russian workshop in Cochin, in which I talked about the same issue about global warming as a threat. The Russian scientist who led his team told me, no, for Russia, global warming has benefits. And he was partly right, because Russia is a cold country and the agriculture is affected by cold weather. So if it gets warmer, Russia, of course, will partly benefit. But he was wrong, because the very next year, Russia had a massive heat wave where the temperature was 20 degrees above normal, like what happened in British Columbia last year. And forest fires were there everywhere, and they were uncontrollable. Okay, so even for Russia, global warming is not all good news. There is good news and bad news, and the bad news dominates. Okay, and because of forest fire, large areas of Central Asia were covered with smoke and forest fire, which could be controlled by human beings. And I want to inform you, these areas are much larger than the area of Karnataka, huge areas, which we cannot imagine because this map doesn't show the actual outline. Now, in the last 2 years, the total area burned by forest fires is 6.7 million hectares in Russia and 3 million hectares in Canada and America, North America and Canada, and 4 million hectares in Australia. From Australia, very bad heat wave and forest fire. Now, these are going to happen more often. And these are something which you cannot control with fire engine. These are completely uncontrolled fires. Fortunately, India have not had it because we don't have too much forest. We have already removed all the forest that is there. So we have not had this kind of large area burning. Now, you must recall that the main cause for the global warming is increased CO2. There is no doubt about that. But when we come to Indian climate change, we have to worry about not only CO2, but also air pollution, which cools the atmosphere, interestingly, and deforestation, which causes local climate change, and of course, urbanization, like in Bengaluru. So when we talk about climate change in India, you have to factor in all these factors. We just can't blame CO2 for it. Now, due to climate change, there are a lot of negative factors. One is agriculture. So our agriculture was developed over the last 10,000 years to exploit the warm climate we have. But if the climate gets too warm, the crops suffer and our yield will go down by about 10%, okay? Especially in unirrigated areas. While in developed world, the higher temperature like in Russia and Europe, higher temperature will mean less frost, so their yield will go up, and anyway, most of the areas are irrigated, they have no problem. So this is a major concern for India, that our yield will go down when our population is still going up. Second thing is extreme events. So extreme events have increased rapidly in India, 50% in the last 50 years, okay? And this is rainfall greater than 100 millimeter per day. And all of you know in Mumbai, in Bengaluru, in Chennai, how 100 millimeter per day rainfall, we are not able to handle. Our urban planning is so poor, our governance is so poor that 100 millimeter rainfall per day causes huge floods in urban areas. So this is going to increase. Why is it decreasing? Now, there are two reasons. One is, of course, the classic Clapeyron equation, which shows that humidity goes up exponentially with temperature, this graph, okay? So for 5 degrees increase, you will have 11 kg increase in 11 gram per kg increase in humidity. The second thing is more critical. As the humidity goes up, atmosphere becomes more unstable because water vapor has a molecular weight of 18, air is 29. So when you put more water vapor in the atmosphere, it becomes less stable and it starts convecting more. So you can see clearly in this observation from Pacific Ocean, when the amount of water vapor goes up about 60 millimeters, that is the total column water vapor, the rainfall starts increasing very rapidly. It's almost vertical line here. For example, at 65 millimeters, there is about 0.5 millimeter per hour, and at 70 millimeters, it is 4 millimeters per hour or 5 millimeters per hour. So almost 10 times. That's what is happening all over India. When the humidity goes up beyond 64, 65, then extreme rainfall events occur, and these occur in very, very small regions, and these are not easy to predict. Right in Bengaluru, about a few months ago, a region called Yelahanka near the airport, the rainfall was above 100 millimeters per day, while in the Indian Institute of Science, it hardly rained 5 millimeters. So huge gradient of rainfall is also there. So this is the thing which is the most serious problem for India. And if this kind of rainfall occurs in the Himalayas, there are large landslides. And we witnessed that in 2013 in Kedarnath, this kind of disaster. Now, if you look at the last 20 years of disaster information, globally, 1.65 billion people affected by flood, 1.43 billion by drought, almost 700 million by storm, and much lesser people due to heat waves and earthquakes. So this is what is going to continue to get worse as we go further. Now, the point I want to make is we came out from last ice age to the present climate quite rapidly, but we are going to move from present climate to some other unknown future climate even more rapidly because we're increasing CO2. That's why in Paris, all leaders of the world agreed that we need to control the amount of CO2 we are emitting. And mainly because there are things which we don't fully understand. For example, Greenland ice is melting rapidly. We don't know at what point it will completely disintegrate the entire Iceland sheet. Why is that? Because the models we are using are very simple. We only talk about ice melting. We don't have a model for disintegration. To do that, we have to go to Greenland and Antarctica and actually watch how ice disintegrates. They are doing it, but still it's not in a model. These two are the most frightening possibilities. And next is, as the ice melts and goes into the water, the ocean circulation starts weakening. Okay, this is called the Atlantic Meridional Ocean Current, which depends on the density difference between Greenland and Antarctic oceans. And as the ice melts and falls into the ocean becomes less dense and the circulation weakens. Okay, and another threat is that the Amazon forest might disappear, which is a very serious issue. So it's a major source of oxygen. Now, this is what I'm talking about. When ice breaks up in Antarctica and Greenland, it actually disintegrates. We don't have a model for this. This is very catastrophic event. This is not a gradual event. And we don't have any model will only talk about gradual melting of ice, not this kind of catastrophic melting of the glacier. And that's what changes the ocean current. Now, if you look at the model prediction about the weakening of the Atlantic current, it is showing it is weakening already. Okay, from 1950 it's been weakening. Red is the model and blue the observations, matching quite well. And so if we continue on this path, this ocean current will gradually stop, and that will have huge consequences to climate everywhere, because this ocean current carries heat from the tropics to the poles. If this stops, tropics will get very warm and the region around Europe will get very cold. Okay. Now, the another major threat, of course, is that as the temperature in the Arctic region warms by 4 to 5 to 10 degrees, then methane trapped in the soil called permafrost starts coming out, and it will start releasing methane. So there are methane fires going on right now in Russia, wherever methane is leaking out. So this we don't understand how much methane is there and how much will leak out. Having given you all this frightening scenario, the question you should ask it, what should the world and what should India do? Okay, that's the first question we have to answer. Now, the problem is, India is not a major emitter of CO2. 50% of the emission of CO2 is from China, Europe, and United States. They contribute to most of the increase in carbon dioxide. India contributes about 6%. Okay, but we still have to be part of the negotiation because we will be the most affected by it. Okay, although we can say we are only contributing 6%, we will do nothing because you guys are the culprits, but that's not going to help. So our government was essentially compelled to take part in negotiation because we know that if the others don't cooperate, the people who suffer most will be us. Now, if you look at the global emission of carbon dioxide, the highest is China. China is approaching 12-13 billion tons. India is around 2 to 3 billion tons. Now, all the developed world emitting much more than India, but their emissions stabilize because they already developed. They don't need to put up new coal power plants. They don't have to spend a lot of money in infrastructure. So they will gradually start declining. So they are worried that India and China will contribute to increase in the future, which is true. But they have to take the responsibility for what they did in the past 100 years. And that's what India has been complaining for the last 30, 40 years, that you need to take the blame and do something about it. Okay. Now, the negotiation in Paris and in Glasgow is now how to reduce emission from around 35 gigatons of carbon dioxide back to zero as quickly as possible. Okay. Now, we already lost time because negotiations are going slowly. So we have gone to 2020. Now, what the IPCC would like is to bring it to zero by 2040, but that's not possible. That would demand 9% decline per year, which is practically impossible. So it will happen much more slowly, which is what we are negotiating. Now, where are we now? If you want to be in the 2-degree warming pathway, at least 60% chance, you have to be on this black line of CO2 emission. Now, China is already emitting around 20 billion tons. And this includes everything, not just fossil fuel, it includes deforestation, so many other things. And it also includes methane and what's called equivalent CO2. It also includes methane and other gases. So that's why numbers are higher here. Okay, so the point is that by 2030, people expect India to go to 10 billion tons, China to 20. So after that, all of us have to drastically reduce. And this is called the carbon space. So only so much carbon is left now. And since we are moving slowly, we will have only so much left by 2030. So this is a tough challenge, but we have done the damage. We have to face it and we have to learn to change. Now, if you look at the CO2 emission from different sectors, the highest is electricity and heat production, about 25%. Agriculture also contributes because of use of fertilizers and tractors. Buildings contribute due to heating and air conditioning. Transport contributes a lot, we all know that. And other industries, cement also contribute. But our focus has to be mainly on electricity and transport because that can be done quickly. Now, in India, I've been arguing for solar for the past 40 years, but people told me I am being too idealistic. They said renewable energy is not reliable, is inefficient, it requires too much land. India does not have enough land, and availability of solar is very low, and it's expensive. Now, I agree that 40 years back it was true. When I started this campaign, it was true that some of these were true, but not anymore. About 10 years back, a very nice article came in Scientific American, written by a professor from Stanford, who argued that it is possible to meet all our energy needs from wind, water, and solar. Okay, and he made a compelling case, and so it's still being debated. There are people who don't agree with this calculations, but it is being debated widely. And secondly, what happened is dramatic. In the last 10 to 15 years, the price of solar generated electricity and the wind generated electricity onshore have fallen dramatically. Okay, this is mind-boggling, a factor of 6. And the cost of solar has gone below nuclear, and nuclear is still going up because of concern for safety. Coal is not changing at all. So today, if you ask any private financial expert, he will say, do not build any more coal power plants, build only solar and wind because they are much cheaper than coal. Okay, so that is the what you call consensus among all the people in the world that building any more coal power plants is completely stupid. Now, this graph of the energy generated, that is the capital cost, energy generated also shows a dramatic decline for both wind and solar. They are similar, and they are much lower than coal and solar thermal. I used to like solar thermal, but solar thermal is somewhat expensive. Solar thermal can also store heat, but unfortunately, it's about 3 times as expensive as solar photovoltaic. So I don't think it's going to make a big headway in the near future. Now you can see that all the nuclear enjoyed very rapid increase in the 70s and the 80s, but after Chernobyl and Fukushima, it has slowed down, while wind and solar have come very rapidly, okay, and have overtaken nuclear. And the solar installed capacity of renewable, it includes solar, wind, biomass, waste, and others have gone up remarkably. Today we have crossed 1,500 gigawatt globally. Okay, just in 14 years, it has gone up 7 times. So can you hear me?
Yes, we are able to.
Yes.
Okay, that's all. Okay, I'm just showing the amount of installed capacity in India, which has gone up rapidly just in the last 4 or 5 years, and is going to increase. So to me, the future in India is solar and wind, but I'm sure a lot of you are here very experienced will tell me that solar and wind are not reliable. India, solar won't come at night, and wind will not be most of the time in the non-monsoon months. Okay, so that is a challenge. But that challenge, this is the energy that's being generated by solar and wind. That energy. Secondly, a lot of people told us that there's not enough land area. But remember that when you put up a solar power plant, that area can also be used for other purposes. You can have multiple use solar power plant region, which have either agriculture or animal husbandry. So it is not necessary that you put up solar plants only in wasteland. Now, here is the point I think is very interesting, that the price of energy storage has come down dramatically in the last 10 years, okay? And it is expected to come down even more rapidly. So if that happens, it will be possible to store the extra solar radiation during the noon period and use it for evening and night. So that is a possibility now, which was not there 10 years ago. Okay, now many remote parts of India now are powered mainly by solar. It is not possible by conventional means. Okay, now I'm going to, I think I have exceeded my time. I'm going to stop here. I'll say that the key thing is climate is changing. People who are denying it are living in a dream world, and human beings are the main culprits. And we know it is bad, and we know we can mitigate it. So it's up to us now to take action to ensure that things do not get much worse. Now, I'm sure that most of you in this audience belong to the Indian Nuclear Society, would expect that nuclear energy will play an important role. Even I felt that it may be true, but in my view, right now, it is not looking that promising. And I'm open to any debate on this issue. Okay, so I'll stop here. Thank you very much.
Thank you, sir. Thank you very much. Dharneji?
Hello?
Mr. Dharne?
Yeah. Thank you very much, Professor.
Thank you.
Yeah, thank you so much for an enlightening lecture, covering all aspects, the human aspects, the natural aspects, and so many controversies about the climate change, and sort of putting very forcefully that the last questions which illustrated the force, which says that yes, everything which was being doubted earlier is now fine. So as you said that you are open to debate, and as I see that there will be a lot of questions in spite of your so nice illustration of the things. Probably there might be some questions. I have some questions, but I will keep it at the end. I will not take the advantage of my being the conductor for the question answer session. I will keep it at the last. So the forum is now open for question answers. The participants may please raise their hand, ask the questions, or put it into the chat. Those will be looked into and that can be answered by Professor Srinivasan. Yeah.
Yeah, let me answer the first question I see in the chat, very important. They are saying drastic reduction in solar due to subsidy. No, government has given no subsidy to solar. The cost has come down due to the power of mass production. The beauty of mass production is that as the volume increases, the price will come down. This is shown from mobile phones to television to computers, all of us know it. So this is purely the power of mass production, not government subsidy. Government today subsidizes coal more than solar in India. You know that for carrying coal, the trains charge less than other commodities. So we subsidize coal much more than we subsidize solar.
Sir, can you stop sharing your transparencies?
Okay, I will see how to.
Then we can talk.
Stop sharing. Okay, fine.
Thank you.
Any further question?
Yeah, can I ask?
Sure, go ahead, please.
Yeah, very nice talk, Dr. Srinivasan. One thing is the availability, indigenous availability of your solar PV panels actually. As I understand that we do not have the indigenous right now, the availability. Most of these panels are we are getting from overseas. And I recollect very clearly we talked maybe 2 webinars back from Institute of Science professor, I'm just forgetting the name, from I think NIAS. In fact, he had given a list of the metals which are required, to sustain the storage and the PV panels, and 90% of them are not available indigenously. So what I'm trying to say is that though you have given an explanation that the land is not an issue, we can always have the farm areas or the these animal lands which can be used as a rooftop or railways. But nevertheless, the availability of the raw materials is not going to pose a problem. So that is one question. My second question is, you had also mentioned about these other pollutants like methane or ozone, which are also causing the global heat, but you didn't discuss it. Are they very minor as far as the carbon dioxide role is concerned?
Yeah, let me explain first about methane. Methane is a very powerful greenhouse gas, but fortunately, it is in the range of a couple of parts per million, not 400. Secondly, its lifetime is 10 years. It oxidizes rapidly. So although methane is an issue and under Paris Agreement, methane has to be controlled, but it is not as serious an issue as CO2. Because CO2 has a lifetime of a couple of 100 years. So whatever CO2 released today will be there for next couple of 100 years. That's more serious than methane. And methane is much less concentration than carbon dioxide. That's the main thing. Now, the other part you're saying is right. There are problems with rare metals, but you must remember that once the demand for solar and batteries start increasing, there are a lot of smart people in the world. They are looking for alternative technologies. I can assure you that in the next 10 years, solar cell will not be made only of silicon. There will be other, for example, the rapid development in the solar PV technologies. There are ones coming up with don't depend on silicon. They are not very stable now. People are doing research on it. But I'm quite sure that once the industry knows there's a demand and there is a lack of availability of material, they will look at alternatives. So both of batteries and solar, in 10 years' time, you will see different technologies than what is there today. So that will be driven only by demand. That will not be driven by anything else. So, for example, lithium right now is only produced in a few countries, but there are a lot of lithium available in many other places, but people are already looking at alternate ways of making lithium and also batteries which are not lithium based. As a matter of fact, we want to store energy on a large scale. Lithium ion battery is not the best. You go to what's called flow batteries, and many of them are not lithium based. They have other technologies, and there are many of them. So my view is that because of the decision of the world to go away from carbon dioxide, away from coal, oil, and gas, there will be a push to develop technologies which both battery and solar. And as the demand goes up and the commodity, whichever commodity becomes scarce, people will switch to another commodity. That's going to happen. And past records show this is what happened in the case of electronics. People switch to various other things. So this will happen here also. That's my belief. But I'm not expert in it. I could be wrong.
What is the role of ozone?
See, ozone problem is complicated. There are two ozones on Earth. One is in the stratosphere, okay, which we created a hole and that we have almost controlled now. That is a good story that we managed to find that hole at the right time, and we negotiated very well. And at the time, America provided leadership, which is not doing now, and we are now back to healing that hole. But there is another ozone near the ground, which is due to air pollution. And that is very serious for Indians, because in India, ozone at the ground level is pretty high because of air pollution. And that ozone is not only bad for our lungs, is also bad for agriculture. So people don't know that because of ozone at the ground level in Punjab, Haryana, Uttar Pradesh, the crop yield goes down. So to me, the first priority for India is to control air pollution, because every year 1 million Indians die. Our government doesn't recognize it, but it is true. 1 million people die, but we think the death is due to something else, but it may caused by air pollution. So to me, the first priority for India is air pollution, which is locally controlled, not globally. And along with it, of course, we also will have to participate in the CO2 reduction also. So ozone problem can be managed quite well. And ozone also, in global warming, its contribution is less than a few percent.
Thank you.
Any further question
May
from
I
the
ask?
audience? Yeah.
May I ask?
Yeah, sure.
Very nice exposition, sir. I would have very much appreciated if you also talked about or gave a comment about biodiversity loss.
Yeah, I'm sorry, I had one extra slide which was supposed to, I didn't show it. What I wanted to show was climate change is only one other many problems we face. The much more serious problem is biodiversity loss. As a matter, I personally feel that will pose a greater threat to us, because the way we have destroyed natural things, the COVID problem is partly related to biodiversity loss. So the climate change actually has highlighted the many different ways we have abused the earth. We have caused major ocean pollution. Ocean is becoming more acidic, and the animals there are not able to produce their shells. So there are many, many problems. Climate change is only one small part. So this is a small part of a global problem of plastic pollution, ocean acidification, biodiversity, all of them. But in one talk, I cannot cover all of them. And I'm not an expert on biodiversity, but I can tell you that I was trained as an engineer. I always thought engineers do only good things, but I realized later it's not true. And my understanding of biodiversity and other things came through climate change. Once I understood climate change, I realized how similar problems have been created by human beings with regard to biodiversity, with regard to ocean acidification. And as a matter of fact, the most serious problem, not even discussed now, the oxygen in the ocean is going down, okay, because the temperature rise. And the animals in the ocean, the phytoplankton, if they don't convert CO2 to oxygen, even the oxygen will start going down. It's already going down, but it's going down in parts per million. But if we do not take care of our oceans, we cannot take for granted that 21% concentration we always think will be there. It need not be there. Every year, these oceanic species produce oxygen on which all living things survive. We are not worried about it at all. We don't even know all the details about how it is done. So you're right, that's the most important problem, not climate change. But they're all part of the same issue of the way we have abused the environment for a rapid growth.
Thank you, sir.
Yeah.
Thank you, Professor. Any other question?
Now, somebody in the chat has asked about monsoon. This is my area of research. I didn't have time to talk about. See, all the models show that due to temperature rise, humidity will go up, monsoon will increase. But we don't have too much confidence, because the models we are running today, they don't even get the current monsoon correctly. For example, the model we are running today for forecasting monsoon, that model, the peak month of July, the rainfall it predicts is about 6 millimeters per day, when it should be 9 millimeters per day. So I still have doubts about the accuracy of the forecast for the future. Okay. Now, in the short term, our forecasts are getting quite good because in weather forecasting, even though the model is poor, you can always assimilate satellite data and correct the model so that for 1 week the model does well, then it starts getting worse. So we are having a good forecast only because we assimilate millions of data from satellites. So that has saved us. But if you look at the seasonal forecast, we are not that good. So I didn't want to say anything because our confidence level is not that good, but I expect that rainfall will increase, except in Kerala. So we ran a model with a high resolution, not me, one of my students ran it in Japan. We had a 20-kilometer resolution, which was able to resolve the Western Ghats in Kerala. And that showed that Kerala alone, the rainfall will decrease. And what's surprising is it's already happening. Over the last 50 years, rainfall in Kerala has steadily gone down, although there are extreme events on some days, but overall, the number of dry days has increased. So this is a bad news for Kerala because Kerala agriculture has assumed that they'll get high rainfall, which may not be true 50 years from today. The rest of India, I think, will get slightly higher rainfall. But there may be long breaks. That is what the model is showing. But the models are not very accurate for long-term prediction.
Thank you, sir. There is one observation by Mr. Sushant Kumar, which says that the mean wind has gone down in the last few decades. And should we shift from wind to solar? I mean, what's your opinion on that?
No, that decreases to me. Yeah, there is some decrease, but not sufficient. Yes, the wind energy will become slightly less, more expensive because of that, but it will not go down to 10-20%. Yeah, it is going down definitely. But, in the case of wind, it's more complicated. You have to know the rate at which hourly wind, because wind will also depend on gusts of wind coming in. So I don't know how that is changing. You're right, the mean wind is slightly gone down because the circulation system is weakening overall. That's true. But we may have to place, for example, according to our model, the so-called Somali jet, which comes into India, it is slightly shifting north. If that is the case, then we have to put more windmills in Maharashtra and North Karnataka, not in Tamil Nadu and so. That's what you have to do. So we have to adjust to that. That's true. But I can tell you that wind is not a great resource for India because we get good winds only for 4 months a year. It's not like China, Europe, and America, which live in mid-latitudes, where they get steady wind throughout the year. That's why United Kingdom can switch over to almost complete wind because they get wind throughout the year. We don't. So I think we have to move over to offshore where the winds are higher, but we have not done that yet. I think government is thinking about it. We have to go to about 10-20 kilometers offshore where the winds are much higher than land. But I think India will have to depend mainly on solar because solar resource is much more than wind in India. In wind, only certain places in Karnataka, Rajasthan, Gujarat, and Tamil Nadu are there. Whole of East India has hardly any wind. So we have to worry about that part also.
Any other questions?
I have one question, sir. Is the maritime shipping, that means the exhaust released by the ships all around the globe, a fairly major contributor to the pollution and then subsequently the climate change?
You're right. Now, ships burn the most dirty oil in the world. So ships are major polluters of the. We can see with satellites. Along ship tracks, the air pollution is very high. But as far as CO2 is concerned, they contribute few percent. Both aviation and shipping is not contributing much. I can tell you there is research going on. Both the aviation industry, ship industry is worried about the pressure which is going to come on them. They are going to, as a matter of fact, Japanese are the leaders. They are talking about sailing ships, cargo ships. Okay, I remember that most of the trade between India and the Europe was by ships 300 years ago. We can go back to it. It's only a question of good development technology. So ships are also going to switch to either what they call green hydrogen or maybe a sailing ship, but it's not urgent because only 2 to 3%. The urgent thing is our power production, our steel industry, cement industry, and those are the ones on land which contribute most. And that's one, I think, immediately action will be taken in the next 30 years. Later on, I think aviation and shipping will also have to come in.
Thank you, Professor. I think looking at the time, we can go for one more question from the audience. Anybody interested?
If you permit, I will.
Yeah, sure, please.
Sir, about this wind in India going offshore, I understand that England could go to offshore because the cost of installation of windmills there is low, as the sea is not very deep, whereas in India, around India, the sea becomes very deep very quickly. So you will have to put most probably floating windmills, which are perhaps more expensive than windmills put on the ground.
Yeah, I agree with you. The offshore technology is still developing. It's very new, but it is something which can think 10, 20 years from not in the next few years. Yeah, it's a developing technology. It will be more costly because you have to run power lines from offshore to here. But countries like USA, UK are going ahead. So we have to learn from them. And also we have to do local data gathering to find out, do we really have regions with high winds or not?
Of course, this year,
yes.
most probably England did not have strong winds, so their electricity production went down considerably.
Yeah, that's true. That's it. When you depend on natural phenomena for your power, we have to adjust to it. Remember that both India and China had civilization which lasted 2,000 years by depending only on solar. So to me, I think we have to change our mindset. We have to adjust our way of living to the availability of the energy, not demand that we get energy. For example, if there is more radiation at noon, most of the industries should pick up the maximum of their work at noon time. So we have to change our way of working. We cannot demand 24 hours energy for industries. Industries have to adjust. Because if you're depending on solar and wind, then they are not constant resources. They are variable resources. So Germany has already gone much more on that. And they are showing that, yes, we have to learn how to adjust to it. For example, we're not doing it in India now. We have to price the electricity according to time of the day. The lowest price will be at noon when solar is there, and the highest price in night when solar is not there. That is going to happen, definitely.
Sir, chalte one sun, one world, one grid पर भी कुछ बोल दीजिए.
That is interesting, but only I can tell you the kind of problem we are having with Pakistan and other countries surrounding. Do you think you can have a grid with Pakistan? I doubt it. So I think what is interesting is that we may have links with maybe Burma on this side and maybe Middle East on this side. Yes, we can put underground cables in the Arabian Sea and go up to Saudi Arabia or Dubai. That's possible. But with Pakistan, I have a doubt that.
What happened? Something happened.
The bandwidth is a problem. He's put on his video.
I'm not so sure about right now.
Okay.
Dharneji,
Okay.
can you wind up?
Yeah, I think I will have the last question. Sir, you were talking about the photovoltaic cells or PV technology, and you have shown the graph that the cost has substantially gone down very steeply, and today it stands much lower below than nuclear also. But when we talk about solar power, the solar power and the storage technology go hand in hand. So if we look at the lifetime emissions, CO2 equivalent of the lifetime emissions of comparison, if we do the solar and the battery storage combined with nuclear, then we find that the lifetime emissions are much higher compared to nuclear in case of solar and batteries. So how do we compensate with that?
Yeah, I would say the people who calculate the CO2 emission, it depends on, do you have a paper? I would like to see it because I find, I looked at many papers talking about lifetime emission. It is very sensitive to the assumptions made. So please send me the paper. I'll go through it and give you my feedback.
Okay, sir.
Because
I will send you the reference.
Yeah, please do that because one has to go through carefully how they have done the calculation.
Sure, sir. Certainly.
Yeah. So it may be true, because remember that any manufacturing involves CO2 emission. The only possibility is something new has come up. There are companies in China planning to make silicon solar cells based on solar cells. Okay. If that happens, that's in the future, not today. Today, all the solar cells are made based on fossil fuel power. You are right, absolutely. But future is different. If solar power, as much as China is a leader, so if they have a very large installation and they generate silicon solar cells from that, it will be. Secondly, remember that all the non-silicon technologies are much less energy intensive than silicon. Silicon is a very old technology, 50 years, 60 years old. So my expectation is that in another 10, 20 years, we'll have new technologies which will use much less energy. Even I can tell you, 20 years back, people used to tell me that the amount of energy produced by a solar cell is equivalent to how much energy consumed by solar cell. That's not true anymore because they become thinner. Okay. So like that, I do expect, see, the point is that if there's a demand and if there's a leadership, things will happen. That was lacking in the last 20 years. Today, I'm happy that in spite of all the noise created by the fossil fuel lobby, majority of the world leaders have agreed that CO2 is the main culprit. That is a big breakthrough in thinking. So once that has come, all the banks are now changing. All the people who are supporting fossil fuel are shifting. Once that happens, I have a great belief in engineers can develop new technology, provided they are given the clear-cut guidelines. So I think you'll find as soon as this issue about CO2 emission from solar comes into play, new technologies will automatically emerge. Not today,
right,
but 10 years from now.
Yeah. The paper
but
which
during
I was
transition,
about,
you have to depend on silicon.
Yeah.
That's unavoidable.
The paper which I was referring was about probably 6-7 years old. The technology has changed. And now with the perovskite cells, etc., I don't know whether we will need silicon, etc., and we may be drastically changing the technology. But as of today, the paper, I will send it to you so that you can have a look at it.
Yeah, I agree. As of today, yeah, it may be depending on, yeah, that's true. But we have to look at the future. So all of us see in our own lifetime how rapidly technology has changed, right? I didn't believe 20 years back that we'll have mobile. I laughed at it. I thought, oh, it won't come to India. And it won't come at a price where everybody can have it. So one has to have faith in the...
Yeah, again, problem.
No, bandwidth low.
Yeah.
Its bandwidth is low.
Yeah, bandwidth is low.
Start doing meditation.
Okay. So...
yeah, I think you can wind up.
Now coming to the last part of the webinar, I really thank Professor Srinivasan for a fantastic question answer session, the fantastic lecture, and I hand over to Mr. Malhotra for the vote of thanks. Thank you very much.
Before that, I would like to add that if any other questions are there, you can send an email to me. I'll be happy to answer.
Sure,
certainly.
Malhotra ji?
Yeah, thank you, Mr. Dharne. And yes, I join Mr. Dharne in congratulating, complimenting, and thanking Professor J.Srinivasan for a lucid lecture on the science of climate change, where we, in fact, we saw an elaborate description of the causes and the effect. But maybe in future, we will have more time on the mitigation part of it. And yes, I do agree with the speaker 100% that we have to shift from fossil fuels to renewables. And I do agree with the statement that wind, water, and solar will have enough electricity. But I think being a lifelong soldier of nuclear power, I would not like nuclear to be left behind. And I very strongly am. And I think, like me, many of us in this audience, they feel that we play a very complementary, very important complementary and supplementary role to the renewables. And I think we should not ever think of going alone in each other's company, holding each other's hand. The renewables and nuclear should be able to contribute majorly to the mitigation of this problem. Anyway, I was supposed to deliver the vote of thanks. not comment on the lecture. So once again, I thank the speaker very much, and I thank the webinar subcommittee consisting of Dr. Rama Rao, Shri Dharne ji, and others.
Ramanamurthy.
Mr. Ramanamurthy for arranging this webinar. I also thank the President of INS and all the Executive Committee members of INS for their guidance and support in arranging these webinars. And in fact, today we had a marathon meeting of INS in the morning. And so today's whole day is dedicated to INS by all of us. At this point, I would also like to thank, which every time we thank, Dr. Shimjit Rajgopal of BARC and Shri G.D. Mittal for reaching out with the information about the webinar to masses. I think that is a very important role, as important as the speaker himself. And as is customary, I think at the end of my vote of thanks, I thank all the audience which are present. I think the number I saw was maybe 40 plus today, the peak number. So I thank every one of you. And now people having come to know that it will be available afterwards on the YouTube, I think people take it easy. I mean, rather joining live, they wait that they will see in the YouTube. And now I am very happy to announce about the next 14th webinar of INS, which will be delivered. Don't get confused. We have one Dinesh Srinivasan right now in the audience, who is the former director of BECC. But the next webinar also is to be delivered by another Dinesh Srinivasan, who is chief executive of Nuclear Fuel Complex. He will be delivering the webinar on 22nd January. That means 2 weeks from now. And his topic will be Nuclear Fuel Complex, a center for development and processing of nuclear fuels and advanced materials for nuclear and strategic applications. So once again, I thank everyone, and with a hope to see you after 2 weeks, that is on 22nd January. Till then, bye-bye.
Bye-bye. Thank you.
Bye.
Thank you all.
Thank you very much, sir.
Okay. Bye-bye.
Thank you everyone. Special thanks to Professor Srinivasan.
Thank you, sir.
Okay.
Yeah, thank you very much, sir.